Welcome back to Chemistry 30 Prep. This lecture will start Chapter 2 in your textbook. It's the Diversity of Matter, second chapter of Unit 1, and we will be looking at the 3D structure of molecules. In your textbook, it's pages 46 to 56. By the end of this lecture, you will be able to describe the three-dimensional shape of ionic crystals, and you'll be able to predict the three-dimensional shape of molecular compounds using something called Vesper theory. So we'll start with ionic bonding. For ionic bonding, we've already mentioned that there's a variety or varying degrees in charge separation depending on the difference in electronegativity between the atoms that are bonded. As the electronegativity of bonded atoms increases, the charge separation also increases, eventually reaching a condition where the electrons are no longer shared. Once this happens, ions have been formed and we have an ionic compound. Ions are the structural units of ionic compounds, so they're the smallest unit in an ionic compound, or they're the reason ionic compounds behave the way they do. When we look at the metallic elements, they have relatively low electronegativities, so they end up losing electrons and they end up becoming positive ions or cations. Non-metallic elements have relatively high electronegativities, and they end up gaining electrons, becoming negatively charged, so they become anions. And what ionic compounds are there an attraction between the anion and the cation. So, cations and anions are attracted to each other. They're attracted to each other, and this is the formation of a ionic bond. So, in this process, electrons are transferred from metallic atoms to non-metallic atoms, and it always involves the same number of electrons, or each metallic atom gives it the same number of electrons to become an ion as every other metallic atom in that sample. Same thing for the non-metallic. The non-metallic atoms always gain the same number of electrons. So when we look at the main group elements, atoms lose or gain the appropriate number of electrons to acquire the electron configuration of the nearest noble gas. And usually what this means is Group 1 elements lose 1. Group 2 lose 2 electrons. And the only other one in the first 20 would be aluminum, and it's group 13, and it would lose 3 electrons. For the transition metals, we don't have a theory that's able to predict why they form the ions they form, so we get them from the table. Remember, there's 2 charges, or 2 possible charges, for a metallic so it'll be one of those 2 choices. If it isn't stated explicitly, then it's the first listed is the most common. And ionic compounds can also involve the polyatomic ions or complex ions as well. So ionic structures, in an ionic substance, every cation is attracted to every anion. And so this results in a very tightly organized and regular pattern of atoms called a crystal lattice. And so what we see here is a sample of sodium chloride, and what it shows you is that because of these positively and negatively charged spheres, each atom or each ion is surrounded by ions of the opposite charge. So if we just take a look at this sodium ion here, it's completely surrounded by negatively charged chlorine ions. And the same is true for every chlorine. Every chlorine is surrounded by positively charged sodium ions. If we take a look at the three-dimensional structure and extend it out, it's the same idea. positive and negative charged particles always interchange, if you like. You have a positive beside a negative, beside a positive, beside a negative. And so this is a crystal lattice. And for ionic compounds, the chemical formula represents the ratio between cations and anions. So technically, the formula is not a molecule. There is no discrete molecules in an ionic substance. For example, you can't really call this here a molecule because it's not discrete, it's not by itself. This small little sodium is attracted to 1, 2, 3, there's at least 4 chlorines around it. And the same thing for every chlorine. Every chlorine has 4 sodiums around it. So it's a formula unit, it's a ratio between cations and anions. Now for molecular compounds, their bonding is a little bit different. They don't transfer electrons. So they're only with nonmetallic atoms. They fill their valence energy levels through sharing of electrons, and it's from this sharing that they fill their valence energy level, which means there's a simultaneous attraction between the shared electrons of the 2 nuclei or the 2 atoms. So each atom is attracted to the same electrons. So this means that the number of covalent bonds formed by an atom is limited, and it's determined by the tendency of each of these atoms to fill their valence energy level, or another way of looking at it is it's determined by the number of bonding electrons. The more bonding electrons that an atom has, the more covalent bonds it can make in order to get that stable structure with 8 electrons. As the difference in electronegativity increases, though, we know that the sharing becomes less equal. So as the difference in electronegativity gets larger, atoms don't share fairly when it comes to electrons, and so the bond becomes polar. So for molecular compounds, the atoms don't form ions. Each atom is attracted only to the atom with which it shares electrons, and each molecule is actually a discrete unit. So the shape of the molecule can be determined by something called valence shell electron pair repulsion theory. And so what this shows us is this is an ammonia molecule. It consists of only 4 atoms, 1 nitrogen, and 3 hydrogens, and that's it. This is a discrete unit. In a sample of ammonia, there are millions and millions and millions of discrete ammonia molecules. So if we just compare ionic crystals to covalent molecules, ionic crystals, these are formula units that represent a ratio. In a crystal lattice. When you look at molecular compounds, you end up getting discrete molecules and they generally have little attraction to each other. And this is because particles are not charged. Whereas here, each particle is charged. In this calcium fluoride, each of these calciums, the yellow, are going to have a 2+ charge on them, a static charge, and each of these fluorides are going to have a negative charge. So each particle has a full charge, either a positive charge or a negative charge, depending on if it's a cation or anion. When we look at the molecular compounds, there's no charge because electrons are being shared, not given away. So for molecular compounds, they have a definite 3-dimensional shape, and it's of interest to chemists to figure out what those 3-dimensional shapes are. And so the study of shape is called stereochemistry. And Vesper theory provides a method of understanding and predicting molecular geometries. It requires only two things: that we know the number and the type of valence electrons in a given compound. So, we're looking at the 3D arrangement of covalent bonds between atoms, and it depends on the arrangement of valence electrons of a central atom. So we're always going to be trying to build our structures around a center. And here's the rules. Valence electron pairs arrange themselves around the center atom of a molecule in a way that minimizes electron repulsion, or valence electrons always try to get as far away from each other as possible because electrons are negatively charged, and negative things with the same charge repulse each other. So lone pairs have a little bit stronger repulsion than bonding pairs because it's two electrons. They're not being shared or pulled away from each other by two nuclei, by two atoms, because they're all alone. So they're a little bit closer together to each other and a little bit stronger repulsion. For the purpose of predicting molecular geometry, we're going to treat multiple bonds as single electron groups, but only for determining shape, because all those electrons are going to have the same orientation. So we'll look at a central atom that has 4 bonding pairs, and we'll look at methane. So when we draw the Lewis structure for methane, we see that we put a carbon in the middle. Methane is CH4. The carbon ends up going in the middle with 4 hydrogens around it. When we draw the structural diagram, it looks something like this. Now, this structural diagram, our electrons are as far away from each other as possible on a two-dimensional plane, right? They're each 90 degrees apart because the farthest away they can get from each other when we're only working in 2 dimensions. But molecules exist in a 3-dimensional world. So when we try to arrange atoms around that center, they're going to space themselves around that carbon evenly. And if we take a look, there's lots of space. If you imagine this is a 3-dimensional molecule here, the distance between these 2 electrons across the carbon to these 2 electrons is 180 degrees in 2 dimensions. So what I'm trying to say is these electron pairs are not evenly spaced around the carbon. In a 3-dimensional world, the most space you can get away from each other in terms of electron pairs is a tetrahedron around a central atom. So if we take a look, if we imagine the center of each of these hydrogens as being the vertex of a tetrahedron, or a 4-sided shape. So we got a side here, a side here, and then behind the molecule will be this one. So here's a tetrahedron. It has 4 sides, 1 on the bottom and then 3 sides along the outside. In the middle of this carbon would sit at the center of this tetrahedron. And then the hydrogens space themselves out evenly around that carbon. So it's a tetrahedral shape because the hydrogens are at the vertices of a tetrahedron. The class is kind of a shorthand form of describing the shape of the molecule. So the A represents the central atom. In this case, it would be a carbon atom. X represents all of the atoms around it. So in this case, it's going to be the hydrogen. And so what this means is that when you have one central atom with 4 other atoms around it, you end up with a tetrahedral shape. Now, in order to draw this in 2 dimensions, we use some funky lines here. 2 of our hydrogens we're going to draw in the same plane as the carbon, so they get normal bonding lines. When the line is just a normal line, it means the 2 atoms are in the same plane. The wedge means that this hydrogen is coming out of the plane towards us. And this dotted line means it's going back into the plane or out behind the paper. It takes a little getting used to, but once you get used to it, it's not so bad. And so the dots represent going behind the wedges towards us, and the solid lines are ones that are on the same plane as the carbon atom. One thing to note is that in a tetrahedron, this angle here is 109.5 degrees, which is bigger than the 90 that we had on a plain piece of paper. So you can see that by thinking about these molecules in 3 dimensions, we can space them out even further apart than what you can on a 2-dimensional piece of paper. So now we're going to take a look at, and what we're going to be doing as we go through these is we're going to start adding lone pairs. That's what this 1LP here. 3 bonding pairs, 1 lone pair. Our last molecule had 4 bonding pairs. That was our CH4. The carbon atom had 4 bonding pairs of electrons around it, 1 for each hydrogen. And we're going to see the shape is going to slightly change as we start adding lone pairs. So we've added a lone pair to our central atom. There's our 1 lone pair. And these are our bonding pairs. So when we draw the Lewis structure, we see it has this 1 lone pair. In order to minimize repulsion, our 4 sets of electrons are going to again go around the corners of a tetrahedron. But because there isn't any atom at that top set, we're going to ignore it when we start talking about its shape. So the Vesper class is AX3E. A is our central atom, in this case it's nitrogen. There are 3 hydrogens, and there's 1 lone pair of electrons. That's what the E stands for. So we'd still have our tetrahedron. Here's our tetrahedron. So there's our tetrahedron right there, with nitrogen in the middle. But because this set of electrons doesn't have an atom attached to it, we aren't going to count it when we describe its shape. So we're going to say that it's a trigonal pyramidal shape, and I'll show you where and it's based on a triangle. And our triangle is going to be right here. So it's going to be a triangular pyramid like this. Just draw that line in the back here. So it forms a trigonal pyramid with a triangular base. And for our structure, notice we have 1 atom going away from us, 1 coming towards us, and 1 in the same plane as the nitrogen. So same thing here. Here's our nitrogen, the blue sphere, 3 hydrogens. These 2 would be in the same plane. This one is coming towards us, and this one is moving away from us, or is behind the plane in the paper. Notice that the bonding angles has dropped a little bit from 109 to 103 because this lone pair of electrons up at the top of nitrogen has more push. So it's pushing those hydrogens a little bit closer to each other. So now we're going to get 1 more lone pair in there. An example would be water. Water has 2 bonding pairs, 2 lone pairs. And so again, the same idea. We still get this tetrahedral shape, but notice that 2 sets of lone pairs are now part of our tetrahedron. So we'll put them at the ones that are moving away and the ones that are moving towards us or coming towards us, and that leaves us with 3 atoms all in the same plane. So this shape is called bent or V-shaped. Again, it's AX2E2, so it has a center. In this case, the center is oxygen. There are 2 hydrogens, and there are 2 lone pairs. If we increase the number of lone pairs once again, These are all diatomic molecules because if we only have one bonding pair, then we can only attach one molecule to our center. So they're all linear, they all exist in the same plane. An example would be HBr or FH. Both of these molecules would be linear, and that's with 3 bonding pairs. So if you take a look in your textbook, there you have this table there as well. It's a little bit longer. They have a few more molecules they're talking about, which we'll talk about in the next lecture. But this gives you a summary of the Vesper class and the shape. So AX4 is tetrahedral, AX3E is trigonal pyramidal, and it's based on a tetrahedron. We're going to see that there's another way to get a triangular molecule, but it's not based on the tetrahedron anymore. Same thing with the bent shape. This bent is based on the tetrahedral electron groups. And then one way to really get these molecules in is by looking at the bonding pairs and lone pairs. As we increase the number of lone pairs, we change the shape of our molecule because the lone pairs no longer count towards the actual shape. They don't come into the shape as we're describing it. If you take a look, this nitrogen would have the lone pair somewhere on this side, pushing on the other molecules, and on this oxygen, the lone pairs would be something like this, taking up spaces on that molecule. So now we're going to try some examples. And so before we worry about the shape, we've got to make sure we get a good Lewis picture first. Otherwise, we're not going to know what our central atom is or what kind of electrons are surrounding it. So here we have CH2ClBr. So let's get our electron total first. We have a carbon, we have 2 hydrogens, we have a chlorine, and we have a bromine. So for valence electrons, that's going to give us 4 plus 2 times 1 plus 7 electrons for chlorine plus 7 electrons for bromine. And so when we add them together, we're going to get, what are we going to get? Looks like 20. And when we take a look at our atoms, we have carbon, hydrogen, a bromine, and a chlorine. And the most electron deficient atom is the carbon atom. So that's where we're going to start our Lewis structure. And we're going to bond a hydrogen here, a hydrogen here, a bromine here, and a chlorine here. And now we'll put in our bonding electrons. There's 8. We need 20, so we got to add another 12. I see 1, 2, 6, 7, 8, 9, 10, 11, 12. So, and this makes sense. Both chlorine and bromine had 7 valence electrons. They only need to share 1 to fill their valence shell. So, in order to determine the class, we look at the central atom and we say, how many bonding pairs does it have? It has 4 bonding pairs, 0 lone pairs. So in terms of its Vesper class, it is an AX4 molecule. It has a central molecule with 4 atoms around it, or a central atom with 4 other atoms around it. Notice that these atoms don't have to be the same. In this case, there's 1 chlorine, 1 bromine, and 2 hydrogens. But all that really matters in terms of determining its class is if there's an atom besides your central molecule. So it's tetrahedral. And if we needed to draw this, and we'll draw a couple just to get some experience, we have a carbon. We have 2 atoms in the plane. It doesn't matter which 2 you put in the plane. I'll put the bromine on this side just to be different. It has 1 atom moving away. Again, it doesn't matter which one. And 1 atom coming towards. And for our wedge opens out towards the one that gets wider, towards the atom that's coming towards us. So a hydrogen there. And that would be the Vesper diagram for the molecule CH2ClBr. So here we have H2S, and we're going to use Vesper theory to predict the shape around the central atom. Oops, I hit the wrong button. There we go. So again, we'll do our electron count. We have 2 hydrogens plus a sulfur. So 2 times 1 electron plus 6 electrons. So we need 8 valence electrons. In terms of the atoms that we have, there's a sulfur and a hydrogen. And again, this is the most electron deficient. It needs 2. Hydrogen only needs 1. So we'll make that our center. So we draw a sulfur, and we're going to bond 2 hydrogens to our sulfur. And now our hydrogens are happy. We'll fill in our other 4 electrons. There's only 4 spots left, so this one's pretty easy. But there we go. Now our sulfur has 8 electrons, our hydrogens have 2, so this is a pretty happy Lewis diagram. And now we take a look at it, and we take a look at our central atoms. We're looking only at the sulfur, and we're saying, well, it has 2 bonding pairs of electrons to our hydrogens, and 2 lone pairs. So in terms of describing this molecule as a Vesper class, it's an A, X2, E2 molecule. And we take a look at our chart, and we see this is going to be a bent molecule. And so there's a sulfur, there's a hydrogen, and we're good to go. So this is a bent molecule, and it's based on the tetrahedron, so we'll just put tetrahedral in brackets beside it, because there's another way you can get bent molecules as well. Alright, so PCl3, we're going to use Vesper theory to predict the shape around the atom again. So we have a phosphorus plus 3 chlorines, and phosphorus has 5 valence electrons because it's in group 15, plus 3 times 7 valence electrons. So we're going to need 26 valence electrons. Oops, that's not what phosphorus looks like. Phosphorus has 1 lone pair, 3 bonding electrons. Chlorine has 3 lone pairs and 1 bonding electron. So our center is going to be the phosphorus. It's the most electron deficient. Get ahead of myself, and we're going to bond chlorines to the phosphorus, 3 of them. Put in our bonding electrons, and then we start filling in the rest. We just put in 6, we need 20 more, and I think there are 10 orbitals that need to be filled. So I can fill each orbital with 1, and then double them up. So there we go. All of our atoms have 8 electrons around them. We have all 26 of our electrons in there, so we have a good Lewis diagram. We take a look at our center, and we say, well, there's 3 bonding pairs, right? They're bonded to the chlorines, and 1 lone pair. And so based on that, the Vesper class would be A, X3 for the 3 atoms, E. And we take a look, and this is going to be trigonal, planar. Oh, pyramidal, my bad, pyramidal. And it's based on the tetrahedron. And if we needed to draw this shape, we draw 1 atom in the same plane as our center, 1 atom away from this, going behind the plane, and 1 atom coming in front of the plane. This picture, it doesn't matter where you put your lines as long as you have one of them somewhere. The same picture can be drawn like this. It doesn't matter where you put your wedges or your dashed lines, as long as you have one of each. The only difference is, and the easiest way to see this is actually to take some marshmallows and some toothpicks and actually build some of these atoms with the toothpicks and the marshmallows. And what you'll see is these two pictures are exactly the same. It just depends on how you've rotated it in your hand. Example 4. SEHCl3, or Si, sorry. HCl3 and Vesper theory. So first we need our electrons. We have a silicon plus a hydrogen plus 3 chlorines. Silicon has 4 valence electrons, hydrogen has 1, and chlorines have 7. So it's going to be 21, 22, 26. And when we look at our central atoms, we have silicon, we have a hydrogen, and we have a chlorine. Silicon is going to be our center because it's the most electron deficient. So there's silicon. And we're going to bond. Now hydrogens and chlorines are both equally deficient, so it doesn't matter which one we put on first. And it looks like silicon has 4 bonding electrons, so we're going to put 4 atoms around it. And then we're going to fill in the rest of our electrons, and it turns out that if we just fill up our chlorines so they have full valence shells, that adds up to 26. And so all of our atoms have 8 electrons except for hydrogen only has 2, which is fine. Look at our center, and we see that it's a center that has 4 atoms bonded to it. So it's AX4, it's tetrahedral, and we'll draw it just to be again, it doesn't matter where we put any of these things as long as we have 2 atoms in the plane, 1 atom behind, and 1 atom in front. And again, we got this AX4 from it having 4 bonding pairs and 0 lone pairs. So our next lecture, we're going to do some more Vesper theory, but we're going to look at Vesper theory when molecules have multiple bonds. So for example, something like carbon dioxide, when we draw the structural diagram, we know that the carbons and oxygens are double bonded. So how does this affect the shape of the molecule?